The next speaker is David Heckerman. He's also going to talk about heritability estimate to the 34 traits in minority of Uganda cohorts, how related to the previous topic.
Great, so thanks to the organizers for inviting me, and thanks to you all for sticking around through Saturday. I'd like to talk about using linear mixed models to estimate narrow sense heritability. And it turns out that these estimates can be seriously inflated when environmental effects are not explicitly taken into account. And one thing we can do is explicitly model these environmental effects or measure them and then model them, but that can be tedious. And so what we're going to do is use spatial location as a surrogate for environmental effects, similar in spirit to what we just heard. Spatial location is easy to measure, and as you'll see, it's very easy to incorporate into a linear mixed model to estimate heritability. So then, after I show you the model, we'll apply the model to a Ugandan cohort, and you'll see that the corrections to heritability estimates can be quite substantial. So let's look at how linear mixed models can be used to estimate heritability. Before we get to linear mixed models, let's just talk about ordinary linear regression. So let's look at Y as a multivariate linear regression on causal SNPs X, as shown here. Let's assume the effect sizes beta are mutually independent, each having a normal distribution, as shown here. And finally, let's integrate out these distributions over beta. And what we end up with is this expression here, and that turns out to be a linear mixed model. The genetic similarity matrix here is just XX transpose, which means the ijth element of XX transpose is just the dot product of the causal SNPs for person I and the causal SNPs for person J. So that's one simple way to arrive at a linear mixed model formulation. So now we have this model, but we don't have the causal SNPs. So what do? Well, we have to use an approximation, and one of the better approximations out there is to use IBD estimated from phased, long-range phased haplotypes. And so we use this approximation in the work that I'm going to show you. We take the model, we apply it to the data, we use REML, or restricted maximum likelihood, to estimate these parameters, and then we just plug those parameters into this formula here to get an estimate of narrow sense heritability, fraction of variance explained by the genetic component. So this model uses the identity matrix to model environmental effects. It turns out that's not a good idea. And as I just mentioned, what you could do is explicitly measure environmental factors and model them, but that's extremely tedious and sometimes impossible. So we're proposing that you use spatial location as a surrogate for environmental effects. Spatial location is very easily measured, and it's easy to put into the linear mixed model, as we'll now see. So here's the new model with spatial location taken into account. We just have an extra variance component here. The similarity matrix K-loc, basically the ijth element is some monotonic function of the distance between individual I and individual J. We plug that into the model here and estimate these parameters again with REML. And now we have a new estimate of narrow sense heritability. Sigma squared E, the E stands for environment here. It's the multiplier for the spatial similarity matrix, and sigma squared R is the residual, whatever's left over. Okay, so this form that we use for the similarity matrix, spatial similarity matrix, is known as a Gaussian radial basis function. It's used in many applications of spatial modeling. We use it here. There's this parameter in the function called alpha. It scales the distance. We estimate alpha with REML simultaneously when we estimate the other parameters, and it basically reflects the range of the location effect. So small values of alpha have a short range effect. Large values of alpha have a long range effect on the phenotype. We estimate these parameters using a software called FastLim, which is available open source on GitHub. FastLim was originally designed for GWAS, and it is extremely fast. Under certain circumstances, it scales linearly in the sample size, and it can handle sample sizes greater than 100,000, but we adapted the software here for purposes of heritability estimation. Okay, so let's look at the Ugandan cohort. These are 5,000 individuals from southwestern Uganda. This cohort was originally established to look at trends in prevalence and incidence of HIV, but here we're going to use it to estimate heritability. We measured 34 continuous phenotypes, as shown here, several anthropometric indices, lots of blood factors, glycemic control, lipid tests, and liver function. And before we applied the model that I've shown you, we cleaned the data by regressing the phenotypes on age, age squared, and sex, and then reverse normally transformed the residuals. Here are the results. The y-axis is heritability. The x-axis corresponds to these different 34 phenotypes. And the high order observation here is that the uncorrected estimates of heritability are always higher than the corrected estimates of heritability. So here's how I'm displaying the results. I have two bars here, blue bar and red bar. The combined height of these two bars is the heritability corresponding to the uncorrected estimate. The heritability corresponding to the corrected estimate is just the blue bar, so the difference is the red bar. And as you can see, for many of the phenotypes, the height of these red bars is quite substantial. So we're seeing substantial correction to the heritability estimates when we add the spatial component to the linear mixed model. There's 15 of the 34 phenotypes were significantly different between the corrected and uncorrected estimates. And many of these are in the anthropometric category, lipid test, and liver function categories. Could be random, could be a pattern there. We just don't know. Okay, so why are you seeing this inflation? So imagine we generate data from this model where we have the spatial component, but we fit it to the traditional model, which doesn't have this component. So here we're in a situation with model misspecification. What's going to happen? Well, we're going to generate a signal here from this spatial component, and it's got to be absorbed somewhere in this model that we're fitting it to. So it's either, the signal's either going to go, some of it could go to the identity matrix, some of it could go to the genetic similarity matrix, and to the extent that the signal gets absorbed by the genetic similarity matrix, you're going to see inflation in the estimate of heritability. So we've done these simulation studies, and sure enough, over many different conditions, we see lots of this signal being absorbed by the genetic similarity matrix and seeing inflated estimates, certainly consistent with the inflation that we saw on the real data. So one important point here is that model misspecification can lead to substantial bias in heritability estimation. I guess that's no surprise. Okay, so let's look at this scaling parameter alpha in the Gaussian radial basis function. Remember, this reflects the range of the location effect. Well, there's certainly a lot of variability across these 34 phenotypes. Alanine has a very small value of alpha, which presumably means the effects, the spatial effects on the phenotype are very short range. And then systolic blood pressure on the other extreme has a very high value of alpha, indicating long range effects of spatial location on the phenotype. And it would be interesting to compare the heritability estimates that we get for Uganda with other cohorts. We found a nice cohort where many of the phenotypes that they analyzed were the same as the ones we analyzed. This is a cohort from Iceland, reported by Zeitlin et al. And so we can compare these heritabilities. There were 6 overlapping phenotypes between the two studies, and 3 of them were significantly different. So for height and BMI, the heritability estimates in Uganda are much lower than those in Iceland. And conversely, for LDL, the heritability estimate in Uganda is higher than that in Iceland. So in this short talk, I hope I've convinced you that model misspecification can lead to substantial bias in limb estimates of heritability. It can often be important to model the environmental effects as more than just noise, as just an identity matrix. Doing that carefully, measuring environments, modeling them can be tedious, but I've offered an alternative, which is to use spatial location as a surrogate for these environmental effects. Spatial location is easy to measure and easy to incorporate into the linear mixed model. Now, these results are new. We've only looked at one cohort with 34 phenotypes, but if this sort of result holds up, this inflation that we see, if it holds up, it adds another chapter to the story of missing heritability. Perhaps a lot of this heritability wasn't missing in the first place. Back to this point that model misspecification can lead to biases in heritability estimates. Based on that, we're now looking at adding additional variance components to model heritability to get a better model and hence less bias. Here's some of the things we're looking at. We're looking at a variance component based on whether or not you share the same household, by whether or not you share the same village. We looked at spatial connectivity, but why not look at social connectivity as well? And then we're adding some variance components, more traditional variance components based on IBD2, epistasis, and G cross E. Finally, we'd like to look at uses of different radial basis functions and to apply these models for not just heritability estimation, but for association studies and prediction. And with that, I'd like to thank you for your time, acknowledge my collaborators, and remind you that this software FastLim is available open source on GitHub. Thank you.